Hello, hello. Good evening. Is there anybody? Good morning. Good morning. Good afternoon. Hello, hello. Welcome, welcome. Okay. Hi, hi. Who joined for the first time? Say hi. Can you type where you're joining from? Which country? Your name, right? Yeah. Ecuador. Wow, that's far. Hi, Marcelo. Wow, Mr. Adam, Aryan, Lucille, hi. Wow, Indonesia. Selamat datang. From China, Qatar. Okay, Oman, Algeria. Okay, okay. Cool, cool. All right, Pakistan. All right. Well, thank you. So this is 8:31. We'll start the session soon, right? So today the topic is 10 commandments of process simulations. We will have our speaker, Rafael Elias, right? I will introduce Mr. Rafael later on. All right, just some housekeeping. Can you confirm you can see my screen, right? Can see, right? Yes. Yes. All right. Okay. Uh, right. So this is just some announcement, housekeeping, right? I think most of you already in the email list, but if you haven't, we will provide this slide deck. You can scan and click also to subscribe, right? So that any announcement, typically, I also will announce in the email list first on webinar or any other event, right? Right. Also, I think we have lined up. Uh, Today is the first webinar. Sorry, it takes a few weeks to get the first done, right? But actually, the February schedule is already out and it's full schedule, right? So I think we have five webinar in February. So looking forward to see you guys also. So just scan and if you haven't registered, if there's any topic you are interested, just register, right? Okay. Next, yes, we actually make our webinar on demand, which means the past webinar you can watch anytime you want, right? So I actually prepare a guideline how to view the on demand webinar. Then I also provided the list of previous webinar which we have put as a on demand, right? So if you join for the first time and maybe you want to check out the previous webinar, I did a friend's message me this morning. She enjoyed very much Vira's Blowdown. She said this is a very good presentations, right? Right. Okay. So you feel free to check it out, right? And an ask from myself, right? Help us spread the word, right? So if you learn something, gain some value from this session, right? So currently we're actually running free webinars, right? So spread the word, right? You can post on LinkedIn, tag our speaker and myself. You can post, right? What are the things you learn, right? Maybe the one thing you learn from this session, right? So you can also share any future webinar post to your network. Okay. Thank you. Terima kasih. Arigato gozaimasu. All right. Okay. A little bit advertisement. Okay. So I created December, right? I make a goal of myself to create a small, very short, half an hour online course, right? This is for high stream reporters. So you can get it for free. You can just scan or click to sign up and get the free course, right? So let me know how you feel about it. Do I speak clearly? My audio, my video, etc. Right? I call the platform the Curious Engineer Academy, right? So this is my first course. Hopefully, I can create more and work with team up with other experts to actually bring a good quality course also, right? All right. I think okay. Housekeeping, right? So I think for those who join for the first time or just a reminder also, so we have a tab on the right, chat, right? We have Q&A. So if questions do post it on the Q&A, it's much easier for us to track the questions, right? Otherwise, it get buried in the chat, right? Then also we have Rafael has made the handout available, right? So this handout is available. I've made the PDF, and now I'm going to make it available so you can download, right? Can you see in the chat? Can you see in the chat? Can you download? Can somebody say? I should not say. Yes, can download. All right, all right. So that's um the slide deck, right? Thanks to Rafael for sharing that. So pay attention. I think this topic is going to be very exciting. The Ten Commandments, right? Ten Commandments, right? So let me. Okay, this one not so important, but for those who join for the first time, hello, I'm Fauzi, right? So I spent most of my life in engineering, right? I started in company, EPC company, McDermott. I spent there for 10 years, work in mainly in Indonesia for 4 years. I spent the rest, maybe another 6 years in Singapore, spent about few months in Dubai. So that's my first job, right? Then after that I continue, but from I'm moving backward, not backward. Means from EPC detail engineering, then I moved to feasibility study, right? So I joined Wally, right? Doing more from but the industry from upstream moving to refinery chemicals, right? Also moving the industry, right? Then also I joined the consulting last time is called efficiency, doing due diligence, feasibility study, financial modeling, right? Spent 1 year with operating company for park operating terminals, right? Then since 2019 I've been with Aspen Tech, right? So currently I'm managing the team of solution consultant for Southeast Asia and Australia, right? Okay, so if you see me on the road or in your meeting or in your country, say hi, right? Okay. All right. So this is the important man, right? Hey, okay. Can everybody type? Let's welcome Rafael first, right? Hello, Rafael. Can type hi, Rafael. Hello, Rafael. Let's give Rafael a good energy, right? We give good energy, so Rafael can actually give us a good presentation. I'm sure, right? Hello, all right. Who know Rafael before? I'm sure because I think a lot of, I mean, Rafael is very well known in the uh, process simulations world, right? I'm sure the network. I'm sure a lot of fans from Rafael also joined this webinar, right? Oh, thank you. That's good. Good energy, right? So let's introduce Rafael. Hi, Rafael. Right. So Rafael is the founder and principal engineer of East 101, right? A Malaysian company specializing in process simulation based solutions for oil and gas industry. Just East 101 is also our partner, Aspen Tech partner for implementation service provider, right? So with over 35 years, he has worked extensively on optimizing production system, pipeline, refineries, and petrochemical facilities. Rafael's expertise include simulation technologies, flow assurance, compressor surge study, carbon capture projects. Right, he has co-authored chemical engineering process simulation, right, published by elsewhere. deliver training programs to equip engineers with practical simulation skill. He holds a Bachelor of Science in Chemical Engineering from Syracuse University, New York, United States of America. Is a registered professional engineer with the BEM and a chartered engineer and a fellow with IChemE, right? Rafael serves IChemE Malaysia chair and is a member of the BEM Engineering Accreditation Council. He also mentors future engineers as an adjunct lecturer and industrial advisors at several Malaysian university, right? All right. Welcome, Rafael. Thank you for being here, right? Yeah. All right. Rafael, you can test mic. You can. I can't hear you. Eh?
Can you hear me okay?
Can you hear me okay? Now I can. Yes. Everybody say hi, Rafael. Oh, cannot say. Only type. All right. I will pass now. I will stop my sharing. Right. So I'll turn off my video also. Right. I mute my video. Yeah, I give it the floor to you. Rafael, you can share screen.
Okay. Um, okay, I'm trying to share my screen. Hold on a sec. Okay. It's not big enough. One moment, huh? I have to juggle this a bit. I'm going to activate the slide. Okay. Can everyone see the slide deck?
I can see, but it's not on presentation mode. It is not on presentation mode yet.
Okay. Let me, maybe I'm not sharing the right. Hold, one moment. Everything went right when we were doing the the test run. Right?
Testing the dry run. Yeah, it always happened. All right, it's okay.
Okay, one moment.
All right.
There you go. Share. That should get the slide deck now.
It is now.
Is that working okay?
Right. Yes. All right.
Okay.
I can see. Perfect.
Okay. Well, thank you so much for having me.
Rafael, sorry to interrupt. Just click hide on the that white window. Just yes. Yeah. Perfect.
Is everything looking and sounding okay, Fauzi?
Yes.
Okay, great. Well, I'd like to thank you very much for inviting me to present on the series of webinars, the Curious Engineer webinars. I also like to thank you for organizing all these Curious Engineer webinars. I think it's a great service to the community. So kudos to you. Everyone give like a thumbs up to Fauzi. I think he's done a great job with this. Yeah. So thank you very much also for the very kind presentation. So without further ado, I'm going to just launch into this presentation, which I've called the 10 Commandments of Process Simulation. Now, the reason I put this slide deck together, this also appears as a chapter in the book that I had contributed to, the Chemical Engineering Process Simulation. The reason I put this together is because throughout my career, I always encounter people starting to do starting to build models, and sometimes perhaps not getting the right idea in constructing the models, or using the wrong software, or perhaps misinterpreting the models. So what I did was I just put together this short 10, I just put together these 10 items. I use that whenever I get like a new engineer, or whenever I'm giving like a little lecture to universities, to some of the students who might be kicking off their final year projects and using simulators. Just like 10 things, a checklist of like 10 things to look at before actually starting to build their simulation model. Yeah. So before I go on, I'm just going to give like a bit of a introduction. As Fauzi had mentioned, I've been working for quite a while. Started my early career working at some simulation companies that you may be aware of. Um, SimSci, that's a company that wrote Pro 2. Hypertech, that's a company that wrote HYSYS, and then later acquired by AspenTech. And actually, even before that, I used to work for Petronas for a bit, for about 4 years. I started East 101 way back in 2003. And we focus primarily on process simulation based uh, advanced process solutions. So we're based in Kuala Lumpur. Well, actually, we're based in this place called Shah Alam, Malaysia. But I always tell people that we're in Kuala Lumpur because everyone in the world knows where Kuala Lumpur is. No one knows where Shah Alam is. When I say I'm from Shah Alam, people immediately assume that I'm from Pakistan. So I just say Kuala Lumpur. And I think you can probably tell by our GPS coordinates where I got our company name from. Yeah. So we're about like 101 degrees east and about 3.08 degrees north. That's our GPS coordinates. Our main office is here in Chalam or Kuala Lumpur. We've got offices all around the world: Houston, Ghana, the UK, Australia, Indonesia, and Thailand. So we're a tiny team. At any point in time, we might have about 15 or 16 engineers. Currently, we have about like 15 engineers and about 11 are process and process simulation engineers. Yeah. So our areas of expertise tend to lie within advanced process simulations, coding. We do some software development, and lately we're doing machine learning, quite a lot of machine learning and AI type applications, um, hybrid solutions, and things like that. I can't get away from AI these days. So, what kind of work we do across this? If you take a look at any of these facilities or hydrocarbon processing facilities. Our main area of expertise tends to be within the oil and gas and hydrocarbon processing industry. We do our work across the various life cycle parts of the overall industry, all the way from like providing some assistance for new opportunities, concept select, front end engineering detail, all the way up to operations. So I'm not going to give you too much of a sales pitch, but just to give you a rough idea, these are some of the things that we do: compressor surge analysis, blow down heat management, heat exchanger tube rupture, water hammer, flow assurance, multi-phase fluid flow, heat exchanger design troubleshooting, um, operator training simulation, operator trainer, operator training system development, all across the board. But our core, I guess, most of the work that we do, maybe about like 90% of the work that we do, tends to come from the oil and gas industry, topside facilities, compressor analysis, controls analysis, and flow assurance. Yeah. Uh, Another large chunk of our customers come from downstream refining. So we do quite a bit of refinery type simulations, crude towers, fractionation systems, conversion units, reformers, hydrotreaters, etc. Yeah. So as I promised, I'm not going to get into much of the um, sales presentations. Our expertise, I guess, spans, or the work that we do spans from subsea reservoirs all the way up to petchem. So I like to say that we provide services from pore to shore and more. It's just a list of some of the customers that we work with. So most of the operating companies: Shell, Exxon, Petronas, the engineering outfits, Worley, Aker, Technip, Toyo, and pretty much most of the FPSO companies as well, like Bumi Armada, SPM, and BW. Yeah. Okay, no more sales. We'll start talking about this 10 commandments and how these can probably benefit you before you start doing a simulation. So think of it as a checklist of 10 things to do. So with regards to this, first thing I'm going to talk about is process simulation. Why do we typically use process simulation? What do you typically use it for? Where it comes into play? Yeah. and then I'll launch into this checklist of 10 things to do before starting a simulation. Okay, so the objective of this module is to, I guess, understand the role of what sort of understand the role of process simulation in our day-to-day process engineering, and have a grasp of some of these best practices before we start doing a simulation model. Yeah. So firstly, why do we use process simulation? If we take a look at the life cycle of an asset, this can be an oil and gas asset, this can be a hydrocarbon asset, or any kind of processing facility. If we take a look at the life cycle of that, we typically start off from some kind of a new opportunity. So this might be like a new field discovery or development. For example, you've got the Hammerhead project in Guyana. You've got the CCS projects happening in Malaysia and all over the world. So these are new opportunities. You typically be looking at doing some feasibility studies or conceptual design analyses for these new opportunities. Later, you have like a front-end engineering or basic engineering, where you start taking a look at the process in a bit more detail, getting a bit more definition on the cost. You'll be doing some equipment sizing in terms of power requirements, duty requirements. You start looking at the equipment lists, looking at operability, perhaps from a preliminary perspective, and start taking a look at like safety and HAZOPs. Detailed design, obviously, you're going to get a bit more, significantly more detail on the equipment sizing. By then, you should be able to start putting together equipment lists so they can start identifying vendors, etc. You'll be taking a look more at the operability and controls of your system. So you'll be, say, for example, if this is a topside facility, you'd be concerned about the compressor operations. You'd want to make sure that there's sufficient protection on the compressors in case they go into surge. So you'll be looking at surge system design, surge valve sizing, anti-surge controls, load balancing controls, and things like that. As you start constructing the facility, typically sometime between detail and detail design constructing, you'll typically be looking at training your operators. So these days, operator training is generally done on simulators, analogous to flight simulators for pilots. We've got our own operating training simulators for operator training systems for operators, process engineers in the facility. And these range from the types of rigor or detail, ranging from simple mimic type configurations, which are just training panel operators, perhaps where to find all the various controls or items or screens are, all the way up to rigorous models, which are based on some kind of a first principle dynamic model, like a HYSYS as an engine connected up to like an HMI, either like a emulated HMI or like a direct connect to a something which is more consistent with what people are using in the control room, like a hot spare or something like that. Then you'd be, after construction, you'd be looking at the commissioning and starting up your facility. Operation, once your facility is operating, you'll be looking at monitoring its performance, doing some optimization, planning, troubleshooting. Later, as the facility starts to age, you'll be looking at doing debottlenecking studies. We're looking at essentially potential bottlenecks or choke points. If you want to perhaps change your feedstock or increase your throughput, you want to know how your facility is going to respond to that and to determine whether or not you need whether or not you need to make any changes. Yeah. Decline, you'll start looking at some form of decommissioning. So through every part of this, there will be some kind of computation and simulation that's required. New opportunity, when you're looking at feasibility studies or feed, you're generally going to generate heat and material balances. with using a steady state simulator. Or when you start designing your equipment, you might be using some rigorous design tools, like if you're, say, for example, if it's heat exchangers, you might be using Aspen EDR or similar tools, HDRI. If you're taking a look at multi-phase fluid flow, you might be looking at Olga, things like that. Yeah. So across the board, you're going to be using all kinds of simulation tools. Okay. So why do we use these simulation tools? Well, when I was going to school, we didn't really have commercial simulation software, so we had to do a lot of computations by hand, and they were extremely lengthy, and they're kind of limited in terms of the type, the kinds of studies that you can perform, um, because you're doing things by hand. It's not really easy to run through a lot of parametric studies or case studies for you to get like a better idea of some operating boundaries and things like that. So back in I guess in the 80s and earlier days, you did a lot of hand calculations or maybe use spreadsheets. It's great from an understanding perspective because you tend to understand things a bit more. But what happens is because of that, you might have a bit more uncertainty. You don't have some of the rigor that you can get if you've got like fast computational models. Hence, one would tend to add more margin to their designs. Yeah, and back in those days, you didn't really have much dynamic simulation capabilities. You had fairly rudimentary dynamic simulation tools back then, or you'd be doing again hand calcs or working with transfer functions. So we've got a plethora of a plethora of simulation tools catering to all kinds of simulation requirements out there. Uh, However, there's no one unified general simulation environment that will cover everything. Um, Even though some of the salespeople might lead you to believe that. So I'm going to be talking about that when we start getting into the Ten Commandments. So there's no one size fits all. A lot of times we need to understand what are the underlying principles, what's the underlying engineering and scientific basis of the system or process that we're studying before we can decide what kind of tool to use. Um, and I stress on the word tool because simulators are just another tool that we use for our day-to-day work. And one of the things that we need to think about before when we're using these tools is to make sure that we understand how to use it and to make sure that we understand how to interact with it, i.e., how to ensure that we need to make sure that the input or the information, the data that we feed into the simulator makes sense, because the old adage goes, garbage in, garbage out. I think nowadays you see that a lot of people are talking about using Chat GPT and AI. Sometimes it works, sometimes it doesn't. Sometimes the response is meets your requirement, is accurate. Sometimes it's completely incorrect, and that all has to do with the way that you phrase your questions or prompt it. Same thing as a simulator. You need to understand how to define your input, understand what the limitations are within the simulator, so that you can understand and interpret the results correctly. Yeah. So we'll cover some of these as things before, some of these items in this coming section that's coming up. So we'll get to this 10 habits or 10 commandments, what I call 10 commandments of process simulation. I think I gave a bit of a trailer. There's like a trailer on the first commandment, I think in one of the LinkedIn posts that Fauzi had put. And let's start off with that. So the first commandment is, or the first thing that you need to do, the first good habit to do is, firstly, you need to understand your objective. It's really, really important. You build a simulation model to meet an objective. And all the models that we work with out there are all custom built. They're all purpose built. because there's not a single framework, there's not a single mathematical framework that can represent all of our business requirements. There's not one single model that can represent all the different kinds of fluids and processes that we can work with. So some examples for this are, let's say, I think if you've used your process simulation tools, if you're using a flowsheet simulator, you'll notice that you've got two types of distillation columns that are available: a shortcut column or a rigorous tray-by-tray column. Actually, if you're using something like Petrosim or something like that, you'll have another third column, which is like a yield column or something like that, which is used for planning. So you have these types of distillation columns or algorithms available in your simulation package. Which one should you use? Yeah, should you use a shortcut model or a rigorous tray-by-tray model? Well, it depends. You sometimes might use a simplified unit operation like a shortcut distillation to initially get some kind of a preliminary material and energy balance for your flow sheet, or you might use that to perform like an estimate of, let's say you wanted to put together a rigorous distillation column to give you an idea of the number of trays or reflux ratio that you might need for that. So depending on what your objective is, you might use a different kind of simulation tool. Another example would be, should I use a steady state simulation or should I use a dynamic simulation? And again, it depends on what you want to do. If you're doing, say, for example, like a first pass adequacy test, adequacy check for an existing facility, would you use a steady state model or a dynamic model? And that would really depend on what stage of the adequacy check that you would be working on. First pass, you might do a steady state model. Take a look at the equipment that you have in the system. Say, for example, if you've got like heat exchanger, you might want to model the heat exchanger in a rating mode. Distillation column, similar, you turn on rating, and then you might change your feed and identify bottlenecks. Yeah. So you just use like a steady state model for that. You take a look at the flow rates and identify if any of the rho v squared or kinetic energy terms at your piping or nozzles may be breached. So I think if you use tools like HYSYS, so I don't mean to be plugging HYSYS so much. I'm not getting any. I'm not endorsing them for any benefits, but it just so happens I tend to use quite a bit of HYSYS and Unisim. So these tools have a lot of rating type functions, which you can use, typically would use to perform some debottlenecking or adequacy type checks. Yeah, I think there's like a rho v squared calculation for pipes to check to make sure that your piping is adequate. I think Symmetry or Icon has this functionality as well. Yeah, so it's important to understand what the objective is, and then once we understand what the objective is, then we can take a look at the different types of functionality that's required. Once we understand what the functionality is, we can decide what sort of software tool to use, or if we have a particular software tool, we can decide what sort of features or functions we need. Yeah, so that's the first commandment: know your objective. The second, before you start working with any kind of system, it's really important to draw an envelope around your model boundaries. Identify your battery limits, identify what's in the scope of your model. I think this is the very first thing that you probably do when you go to engineering school. If you go for a chemical engineering degree, the first class that you take is probably the first chemical engineering class that you take is probably going to be heat and material balance. And the first thing you're going to do is you've got like a flow sheet, a schematic, or PFD. First thing you're going to do is you're going to identify your boundaries, your envelope around there. Yeah, it's really important. Another thing that I also recommend, highly recommend, is sketch your system out by hand. I find that when I sketch things out by hand, I have a better feel for the overall process and what's going where, as opposed to just grabbing a PFD or a PNID and using that as a basis to plug into my simulator. I might start with a PFD or PNID. I'd have a hand sketch. By hand, back in the days, well, I've got a pencil, I would sketch it out by hand, but these days you guys might be using Visio or some other sketching tool to sketch things out yourself, because sometimes you need to take a look at your PFD and PNID and reinterpret that into a PFD that you're going to be able to use in HYSYS. For example, if you have PNIDs or piping instrumentation diagrams as a basis, you don't need to include a lot of that equipment in the simulation model. Yeah. So you might not need to include like certain relief devices or drains, drain lines in your simulation model as a first pass analysis. So typically what you do is you just sketch out the parts that are of interest and then utilize that for your simulation. Use that as a basis to construct your simulation model. Yeah. Once you've done that, or before you do that with your PFD and PNID, it's a good idea to draw an envelope to identify the areas of interest. So let's take a look at this system over here. Now, let's say we want to build a simulation with some heat material balance data. And you know something strange over here. Yeah, you notice that I've got a very simple model over here. I've got air and water. We assume that they're pretty much going to split up into two separate phases. Yeah, where I'm not going to I'm going to ignore any kind of like absorption or anything like that. So I've got like a kilogram of air and 100 kilograms of water. Put this in this tank, and I find in this particular drawing, this HMB, I've got like a 1 kilogram of air in, 1 kilogram air out, but I've got about 100 kilograms of per hour water coming in and 120 coming out. So what could be the problem over here? Well, if I take a look at the overall diagram and I draw my envelope correctly, I can see that this system that was initially part of this envelope is actually part of a recycle. Yeah. So this this may sound trivial, but I've worked on a lot of projects where people say, "Hey, I've got missing, I've got more material, or I've got less material in my system. Something's not right." Uh, the, and a lot of times it's because the boundaries are not drawn correctly. Yeah. So in this case, you can see that the initial picture that I showed you was actually the red line over here. Whereas if I take a look at the overall system, it should be in this green envelope. And that section over here, 120, is actually a recycle that's going in, like a minimum flow recycle. So now if I take a look at my boundaries, it makes sense. I've got like 100 kilograms of water coming in and 100 kilograms of water coming out. Yeah. So it's really important to draw envelopes and to understand where we're at with regards to the process. Okay, so that's the second item. The third, here's something that I think is really, really important. It's extremely important. A lot of times when you go to school, the way the education system is set up these days is we start off in a very abstract manner. You start off with maybe a heat and material balance, maybe it's transport phenomena. It's a lot of computation, thermodynamics, and it tends to be very theoretical and abstract in nature. So sometimes you don't really see how this maps into the actual processes. If you're lucky, your university program would have like a good laboratory, and there would be a lot of mapping between the theoretical aspect and the laboratory. Unfortunately, during COVID, this wasn't possible because a lot of courses were online. So a lot of students, very sadly, did not have access to laboratories. And it's really important for engineering and science students to have access to laboratories to enable them to understand how the theoretical concepts that they learn map to actual equipment, yeah, and responses. So sometimes if you don't have that, then you need to have some kind of good imagination to kind of figure out what could be going on behind the scenes. Yeah. So here's a simple example over here, and this might be again a fairly trivial example, but I've got an inlet outlet for this simple process. It's just a valve. And I find over here that I've got my inlet temperature is about 50 degrees Celsius, 50 bar gauge coming in, and about 100 million scuff of gas. And pressure drops from 50 to a 10 bar gauge. And I see the temperature drop as well. Yeah. So obviously, what's going on over here is the Joule-Thomson effect being calculated by the simulator. So should you be surprised? Well, no, obviously, because you see this pressure drop, the first thing that should come to your mind is it's a valve, it's an expansion, a Joule-Thomson effect, and you should expect like a temperature drop. Now, I'm saying this this should be trivial because I've seen situations. I've gone to the plant and I've looked at the valve and ambient temperature inlet of the valve is maybe ambient temperature or the temperature that's coming out of like an air cooler about like 45 degrees Celsius. And I take a look at the valve and the valve is sweating or sometimes there's ice on it. And someone tells me there's something wrong with that valve. It's closed, but there's ice on it. And as soon as they tell me that, I know that there's no way that valve is going to be closed. It has to be leaking or passing because of the Joule-Thomson effect. The temperature drop when you start having an expansion and the pressure drop crosses a valve is essentially an isenthalpic pressure drop, and it results in a reduction of temperature. Yeah, for most fluids. In some fluids, it goes the other way around when you're talking about monoatomic gases. Yeah, but now this is a general case where you might have methane or other types of fluids, other types of gases. You might expect this type of phenomena. So it is due to your Joule-Thomson effect, and you should be able to map this with what's going on in your facility. Most of the time in your plant, a lot of valves might be insulated. In some cases, if they're not, you might see what's called a sweating. Sweating just means that the valve is getting cold and you're getting like condensation on it. Yeah. So it's really important to understand what's going on in real life before we map it into the so we can map it to the simulator. Number 4, this is something that's really important as well. Now we spent a lot of time in uni. Minimum time is about 4 years. Some people spend more. 4 years, and then you've got foundation. And a lot of times, if you take a look at the school curriculum, engineering school curriculum, you start off with some fundamental science classes that might either be in foundation, or if you're in the US program, that might be in your first year. Chemistry, physics, calculus, that would essentially start laying down the framework for things to come. Then you'd start off with some of the fundamental engineering applied science classes like thermodynamics, transport phenomena, reactions. And then you start getting more and more closer to what you're going to be working with when you're out in the field. So you've got unit operations, design, safety, and things like that. So when you're working with these kinds of when you're taking these classes, you find that you're going to be working with, you'll be introduced to a lot of different types of mathematical models. Yeah. If you're working with a gas and you want to figure out what its density is or what's going to happen when you compress the gas, you obviously might need to work with some kind of an equation of state, like Suave-Ridley-Kwong or Peng-Robinson. So if you're working with a gas compression system, you need to make sure that whatever tool that you have will have some form of equation of state. These days, everyone's looking at carbon capture, CO2 compressors. If you just use your Peng Robinson SRK straight out of the box, you might not get very representative densities or behaviors or enthalpies for high CO2 fluids. Hence, you might go with something like GERG 2008. So we understand from our uni days that we are using some form of equations of state. When we start using our simulator and we're working with a gas phase system, we need to make sure that the simulator has these various options. Yeah. So it's very important to understand what kind of mathematical models or physics models are available in the simulator before you use it or even before you buy it. Yeah. So here's a simple example. And I made this mistake when I was a fresh engineer. I was modeling a water, a cooling water system. Yeah. So this was the freshwater cooling water system for a topside facility. So it contained the pumps and the various sections of piping and valves. So one of the analyses that I wanted to do was to take a look at this phenomena of water hammer. What's water hammer? Well, you see this sometimes in your house, right? Sometimes if it's an old house and you suddenly open a tap, you start seeing the pipes shaking or clanking. When you close the tap, you hear it clanking again. So what's happening is a sudden opening and closing. Let's see if you have an open tap or an open valve, you've got your water or liquid flowing through. If you suddenly shut it, that shutting essentially, your fluid has a certain amount of momentum and inertia. When you shut that down, that momentum inertia has to go somewhere because you've closed your valve. So it then gets translated as a pressure wave across your fluid, and some of that pressure wave gets converted into kinetic energy and starts moving and clanking your pipes. So I was looking at taking a look at this water hammer or liquid pressure surge in a system, tried using something like HYSYS, and then realized, was shocked that it didn't work. HYSYS dynamics, for a very simple reason. It does not contain the sufficient the momentum balance for a liquid. It also doesn't take into account the accurate liquid compressibility. So you can't model pressure waves within HYSYS, Unisim, or ICON. You need to use some other kind of tool like PipeNet or AFT Impulse, which is specifically built for liquid pressure surge type computations. Yeah, so it's really important to know that. If you take a look at the Bernoulli equation, yeah, which you probably would have covered in uni in your fluid mechanics, HYSYS, Unisim, ICON dynamics would cover friction and elevation, but there's no momentum or kinetic energy terms. Hence, you can't really use it for this kind of phenomena. You need to work with another tool. Okay. So, as I mentioned, we have a whole lot of different tools for different kinds of functions, and it can get quite daunting. Yeah. So for heat and material balances, you've got your typical flow sheet simulators, Pro2, HYSYS, Aspen Plus, Unisim, ICON. This hasn't been updated for a while. Multi-phase fluid flow. You've got like a Olga, pipe sim, etc. For dynamic, you've got Olga, leader flow. heat exchangers, you've got EDR, HTRI for rigorous thermal design. For flare system, you've got FlareNet, visual flare, all kinds of tools. Yeah, for valve sizing, you've got the various valve sizing utilities within your flowsheet simulators, and you've also got special vendor packages. For distillation column rating, you've got some built-in tools in your typical flowsheet simulators, and you also have, I guess, what's it called? KGNet or something like that. Coke Glitch has their own like package for rating, particularly their systems. So there's so many different types of applications out there. It's really important to understand your objective, the kind of model that you have, the type of physics within that model, and then map it to your different types of products. Yeah. So a lot of times you're going to have some questions. What kind of software do I need to use? Is HYSYS better than Pro 2, or is it HYSYS better than Aspen Plus? The only way to know that is to really understand your objective, what you're studying, and what kind of mathematical tools you need, and to check whether those tools are available in the software. Ask the sales guy. You got to be a bit careful because sales guys will tell you all kinds of things. I used to be a sales guy when I was with Hypertech and Aspen Tech. We were actually multifunctional. We had to do tech work and we had to do sales as well. So obviously when I'm sales, I'm commissioned. So I want to maximize my commission. So I guess maybe back then I might have told people that, yeah, we can do pretty much anything with the software. So be careful when you're talking to sales guys. Okay. So the fifth good habit or commandment is make sure when you're starting your simulation, after you figure out the objective, after you take a look at your boundaries, take a look at the kind of components that you're going to be using, and also how they're going to be interacting with each other. When you know that, then you'll know what kind of fluid package you're going to need. Yeah. Also, you need to understand, do you have a complex fluid? Do you have like azeotropes? Do you have like deviations from Rayleigh law? Do you have ionic systems, electrolytes, association, dissociation? Yeah. So if you have like an electrolyte system, then you might need to choose an electrolyte package. Or in our case, I prefer just to go straight into Aspen Plus and use the electrolytes over there rather than attempt to do it in HYSYS with the Aspen properties. So there's a lot of things that you need to take into account when you're working with the fluid package. Now, there's something over here that I'd like to stress. Understand not just the components, but how they're going to be interacting with each other and what they're going to do. What are the components going to do? So I'll give you a simple example. If you are doing a lot of upstream type of activities, we would use methanol as a hydrate suppression for hydrate suppression. Yeah. Hydrates is when you can get like essentially solid water forming due to the water's interaction with certain types of hydrocarbons, yeah, methane, ethane, etc. And hydrates can form at temperatures above freezing point, your typical freezing point. So what we do in order to eliminate hydrates is we inject methanol. So if you are utilizing, if you're doing some upstream simulation, you're modeling like an upstream facility or starting up a well, typically people would inject methanol, and you can see how that affects the hydrate formation temperature. So when you put in methanol, the hydrate formation temperature reduces. That particular mathematical behavior, or that sort of behavior, is built into certain fluid packages. So I believe if you're using HYSYS, traditionally it was in the Peng-Robinson equation. and I think also SRK. So if you chose your components, your hydrocarbon components, water and methanol, the addition of methanol to your fluid would essentially, you'd see that phenomena of hydrate temperature reduction. Um, Now, if so, that's what you would use. I think nowadays they've also added CPA, a cubic plus association, to address this as well. But essentially, these are some form of cubic equation of state. So if you're working, if you want, if you're using methanol to suppress hydrates, then you need to use one of these applications: Peng Robinson, SRK, or CPA. However, let's say you work in the methanol plant in Labuan or in the methanol facility in Kedah, fertilizer or something like that, and you're synthesizing methanol, and then you're separating methanol, purifying it. You can't use an equation of state for that, because now you're taking a look at the hydrogen bonds between methanol and water. So you need to work with an activity coefficient model, like a NRTL, for example. Yeah. So it's the same molecule, but it's interacting differently. It's doing different things. It's a different process. So we have to use a different property package for that. Okay. The 6. So after you figured out what kind of components you have for your system, and you've chosen the kind of property package, whether using the cubic equation of state or whether using an activity coefficient, the next thing you would probably have to do is to define your fluid. And it's really important to understand the context of your feed stream. Now, a lot of times, I think when I first started off my career as a graduate engineer, I would just take a look at, I'd say, okay, give me the composition of this feed, and I would get like a GC result with components, methane, ethane, propane, some CO2, etc. And I chuck that in a HYSYS or Pro2 or Aspen Plus. But it's really important to understand where that composition came from. And we need to do that because we need to be able to characterize the fluid correctly. If you're taking a look at some results and they're coming out of a GC, you will find that they're always going to be on a bone dry basis. There's no water. Why? Because before you put your sample into the GC, you need to get all the water out. Otherwise, you're going to damage the inside the GC. There's like some tubing with some beads. If you have water in your system, you're going to essentially damage your equipment. So most of the time for a GC, you'd knock all the water out, so you'd have like a bone dry gas coming out. Hence, your GC analysis would be water free. But let's say your analysis was from a facility, from a topside facility, a 3-phase separator, where there is like oil, gas, and water. Well, then you might need to take that dry gas composition and add some water to it, or at least saturate it with water. So that's why you'll find that in some simulation tools, you'll have a saturation function. So if you're using HYSYS or Unisim, Petrosim, you'll find like there's like a saturator object, which will allow you to saturate a stream with water at some stipulated temperature and pressure. Yeah. Okay. The 7th thing, after you know what components you have, it's a really good idea to know what their boiling points are and maybe like kind of arrange them in terms of boiling points. The reason I like to do that is because then I can do some, if I want to do a material balance, or if I want to have an estimate for a distillation column, I can just draw a line and figure out my light key and heavy key and do a simple material balance. Yeah. So I like to know what the boiling points are and kind of arrange them in order to facilitate my me being able to do a quick back of the envelope material balance. Maybe I might use that for like a first pass calculation, or just like a sanity check. Yeah. So sometimes I might check the HYSYS simulation with just like a hand calc. So let's say I have like a 3-phase separator and some of the gas is going up to the compression. I know that my compressors are generally going to be designed for a gas molecular weight, if there's no CO2, for maybe about like 19 to 20 molecular weight. So then I would know where to kind of draw a line. If I have like a mixture of gases, to pretty much draw a line to get send the lighter components up, which might yield that low molecular weight. So I don't need a simulator to do that. I can just look at my boiling points, molecular weight, and arrangement, and just kind of draw a line and figure out what's going to go to the gas side and what's going to go to the liquid side, just as a first pass calculation. Same thing, you might want to do a first pass calculation when you're doing a distillation, when you're modeling a distillation tower. Yeah. Okay. Number 8. This is something which is really important. It's something that I always tell people: keep track of your units of measure. I have, well, you can't see it on this board because I'm doing it dimensionless on this board, but we have a lot of whiteboards in our office, and every time someone does a calculation, I insist that they make sure that they put in the units of measure. Yeah, because it's really, really easy to make a mistake, particularly in chemical engineering or upstream or oil and gas. We work with horrible sets of units. Okay, I might be working like when you're in university. If you're a university student, you'll be doing all your stuff in SI, perhaps. Temperature in Celsius, pressure in kPa, molar flow in kilogram moles, mass flow in kilograms. You know what gas constant to use based on the units. But in real life, that's not the case. Where you're in oil and gas, I might be working with flow rates, gas flow rates, molar flow rates expressed as volumes, millions of standard cubic feet per day, but temperature in degrees Celsius, density in specific gravity, pressure in pounds or bar gauge. So we need to make sure we write down the units. We can keep track of them. So we keep track of them. Because even if you're doing like a simple calculation on the back of the envelope or napkin, just show your units. Units of measure errors are really, really easily avoidable just by having that discipline. My daughter, when she started going to school, I made sure that she kept track of her units. So even when she was in secondary school, she would write all those unit equations out in her chemistry or physics class. So make sure you keep track of your units of measure. If you're using a tool like a standard simulators, you can set your custom unit sets. Yeah, so they'll come with some built-in field and SI units, but you can also create your custom unit sets and utilize them throughout your project. Okay. Number 9. This is something I've talked about earlier on. You need to perform. You really should do a heat and material balance first. That's why I like to arrange the components in terms of the boiling points, so I can send light stuff up, heavy stuff at the bottom. Do it by hand so you can get an idea of the order of magnitude. So let's take a look at this simple example over here. So I think there's a lot of people here who have used distillation. I'm sure Fauzi, at some point in time, he goes and meet the clients, and he probably has to do a bit of tech support. And they'll come and say, hey, there's something wrong with HYSYS. I can't converge my column. I put everything in, but it doesn't converge. Yeah. So I have a case over here. In this particular system, I have a depropanizer column, and I've got like a condenser and a reboiler. So I've got 2 degrees of freedom, and I'm utilizing them by specifying the reflux ratio. And I've got a requirement on my overhead, mole fraction of propane. And I want this at 95%. I'm turning this on. So that means the propane here has to be 95%. And I run this, and I run it, and it doesn't converge. It's not converging. What do I do? Well, I hit reset and run again. Maybe it'll converge. Well, I'll change something. So why doesn't it converge? Well, let's take a look at the material balance for this. Yeah. So if I do a material balance, in this case, I'm doing it in moles. You can do it in mass. It doesn't really matter because there's no reactions over here. So the moles and mass will be conserved. So if I take a look at my feed, this is the flow rates of my feed coming in. 33 kilograms methane, 36 ethane, etc. Yeah. And what I'm going to do is I'm just going to do, I've arranged this in terms of my boiling point. This is a depropanizer, hence propane and lighter has to come up. So what do? I just use this as I draw a line here. Propane's my light key. I'm going to send it to the top. Butane's my heavy key. I'm going to bring it down to the bottom. So if I do this analysis, and let's say I've got a super ideal, just again, it's just a back of the envelope calculation. I send all my propane lighter above. I will never be able to get 95% propane because of this is the amount of propane, methane, and ethane that's coming at the top. Hence the maximum, sorry, this should be mole frac, not mole percent. The maximum amount of propane that can get at the top is 35% and not 95%. Yeah. So if you can talk about maybe 95% could be recovery, but definitely not the composition at the top. So these material balances are really important. So before chucking in the composition, before chucking this in as a spec, it's a good idea to do a hand calc first. And this is really, really important, in particular when you're working with crude oil distillation, because you've got, I don't know, your distillation column will have maybe about 12 or 10 degrees of freedom. You should have an idea of what your product yields are to use as an initial guess before you start your crude tower. Yeah. So it's really important to do these material balances. Okay. So always do material balance first. You can't believe, I'm sure Fauzi or Aspen Tech Support, his friends in tech support must have many man hours of listening to complaints that my distillation tower doesn't converge. Something wrong with your simulator. Okay. And the final and last commandment, plot the phase envelope. It's really critical. Yeah. There should be a reflex for all chemical engineers. There will always, if I will walk around my engineers' cubicles now, I think each one would have like a phase envelope on there. I don't have one on mine, actually. Normally, I'll be looking at something with a phase envelope. So this is really important. So once you have your phase envelope, you have an idea of where your dew points, bubble points are. You can identify regions of retrograde behavior. And what do I mean by retrograde behavior? Well, let's take a look at this. So this is the classic low temperature separator chill gas plant example, which I think is in Pro 2 HYSYS Petrosim Symmetry. I think it's probably coming from the same place back from the 1980s. So what I have in this case, this is actually part of it. Yeah. So there's another section over here where I've got like a separator. You might notice this, and I've got like some feed, maybe 2 feeds coming in. So I'm taking a look at this, and the objective of this unit of this process is to nail down the dew point of sales gas. So it's a dew point control unit, refrigerated gas plant. I put in a rich gas here, and then I chill it to drop out the heavier components, the propanes and the butanes, and then I make a lean sales gas, which I'm going to send to the sales gas line, which should be mostly C1, C2, maybe a smidgen of C3. And I have a requirement that the dew point is minus 20 degrees Celsius. Sorry, I want to find out what is the dew point pressure at minus 20 degrees Celsius at this point. Yeah. So in this particular example, it's a bit different from the case that you typically work with. But now, in this case, what I want to do is at minus 20 degrees Celsius, what pressure can this system potentially operate at, or what would be the dew point pressure. So how would we typically do this in HYSYS or any other tool? Well, you would specify this as a dew point. So you'd put like a vapor fraction. So that'd be blue. Or if you're a HYSYM user, that'd be a star. I'm not sure how many people here have heard of HYSYM, but that's HYSYS's father from the 1990s, written in C. You nail down the vapor fraction as 1 and the temperature as minus 20. And it would calculate the dew point. For all intents and purposes, this is correct. Yeah. So you nail that down, you get a dew point. And the dew point is about 2,962 kilopascals. Yeah. Is this right? Well, let's take a look at this. If I plot this stream over here, the LTS vapor stream on a phase envelope, what do I see? Well, at minus 20 degrees Celsius, I get 29, which is correct, right? So minus 20, I get that point. But look, I also have another point. I've got actually, for one temperature, I've got 2 dew point pressures. Yeah. And this exists. I'm not going to get into this. I recommend you go back and have a look at your thermal book. It has to do with the fact that this is a multi-component system, and I've got this slight bulging region over here. And that's this region here. That's my retrograde region. When you see reservoir fluids, you'll see that this retrograde region gets fatter. So you'll have more than one solution for a dew point pressure and potentially also for a dew point temperature. Yeah. So it's really important to plot things out, because in this case, if this was a homework problem and they ask what the dew point temperature is, dew point pressure is, you actually have 2 dew points. And you'd only know that if you plot the graph out. There's a trick to see. So this number here, 2,962, would be referred to as the dew point of this fluid. 80,000, or this 80 bar, would be referred to as the retrograde dew point. Yeah. So there's actually a trick. If you want to get the retrograde dew point in HYSYS or Unisim, you just put -1, and it show you the retrograde. +1 would show you, if there's a retrograde, -1 would show you the retrograde. You don't always have a retrograde dew point. Yeah. If this is positive, it'll return the dew point. Okay. So that's all I have. I hope everyone's still awake. This last slide kind of summarizes all the 10 commandments. Understand your objective. Draw an envelope around your system. Imagine what's going on. Translate your physical model into a mathematical model. Know what components are involved and how they're interacting with each other. Understand the context of your feed. Do you need to do any feed treatment or blending? Keep track of the units of measure and make sure you always keep track of your boiling points, keep track of your units of measure. Always do a heat material balance first. There's a reason why that subject is the very first engineering class that you take when you go to chemical engineering school. And finally, plot your phase envelope. Yeah. So these are the 10 things that I would highly recommend people to do before starting their simulation. So all of this, you can do this before you even buy or start up your license, or before you consume tokens to run your simulator. Here's some additional tips. Make sure you analyze all the input data. I'm not going to get into data validation, but if you've been working with plant data or experimental data, some data is better than others. Some has errors, some has outliers. You might need to understand how you might treat that data to put into your simulation model. So it's really important to understand the source of data and analyze all the input data. So when you're building a simulation model, you need to allocate some time to do some data validation and workup. Yeah. After you've built your simulation model, it's really important to validate and verify your model. before you do any kind of rigorous case studies or anything with that. If you're doing a dynamic simulation model for a project for an existing facility, for example, it's good to talk to the operations engineers to make sure that what you have in your model is consistent with what they have in the field. Yeah, piping isometrics are consistent. The assumptions that you made in terms of pipes, fittings, equipment configurations, valves, valve sizes, you might want to check. Sometimes you might not have access. If it's a very, very old facility, you might not have any drawings or data sheets. So you might need to go to the facility and then look at the face plates on the equipment to check for things. Yeah. And later when you're writing your report, again, could either be your report for your final year project or a simulation or engineering report. It's always important to communicate and explain your bases and assumptions in your report or documentation, also so that the reader or your client understands what the limitations of your model can be used for. The limitations of the model are the limitations of the model are. Yeah. Sometimes you're going to find as you start going on in your career that you're not just going to be able to copy and paste from your simulator and chuck into a report. You might have to do some post-processing, or you might need to inject a bit of realism into your model. HYSYS, Unisim, Petrosim example for as an starting point. When you have a separator, by default, your gas, the vapor and liquid coming out of the separator are going to be saturated gas, saturated liquid. Why? Because it's a perfect phase disengagement device. There are some functions in there which allow you to have liquid carryover and some carry under, but you'll have limits on that. Are you using a hard spec for carryover or carry under, or are you using some rules of thumb? So it's important to communicate that in your assumptions. Yeah. Okay. So that's all I have for this evening. I'd like to thank you for your patience, and I hope I hope I managed to take a look at some. I hope that this may be useful to some of you students as well as practicing engineers. If anyone has any further questions, you can shoot me an email. I'm at rafael@east101.com, or you can contact Fauzi. He knows where to find me. I'm one of his clients, so he's with us all the time to make sure that we're using the software or we buy more software. So thank you all very much for your patience and attention.
Yes.
And I'd like to open the floor to any questions, should we have any.
Yes, there are some questions in the Q&A tab, right? The first one is from Michael Theo. I feel it's like a statement instead of question. Although high pressure drop cause JT effects, such great temperature drop in simulation shall not happen in real plant because of the mass of the equipment and the pipeline. I think this more of a statement.
Yeah, that's actually that's a good observation, because you've got, say for example, there's two things over here, and that's a very good observation. And this is something that we see when we're doing like a depressuring. So let's say you've got a valve that's closed and then you suddenly open it all the time, like your metal temperatures around there are not immediately going to plummet. Yeah. Why? Because you've got some thermal, you've got a thermal reservoir. So
Yes.
you've got the mass of the equipment, like you mentioned over there, equipment and the pipeline. However, if you've got like a valve, say for example, like one of the cases that I was looking at, we had like a valve, and it was leaking. We had like a temperature drop across due to the Joule-Thomson effect. Now you can't, if your valve is not insulated properly, you will get some thermal leak from the environment into the system. So yes, some of that can be absorbed in the fluid. But bear in mind also sometimes that the the flows might be really fast that you might not also have enough residence time to transfer the heat. So your fluid temperatures may drop, but your metal temperatures may not, because of the thermal reservoir and because of the heat coming in from the surrounding. So that's a good observation. Thank you, Michael.
Right. Second one is from Novian Buyung Pamungkas, right? He say, in my case, I always find it challenging to translate what I want into simulations. I mean, not all physical chemical process needs to be simulated, right? Which is true. We have to make some simplifications. However, this might compromise the integrity of the simulation itself. The bottom line, just how far I can trust the simulations, knowing the implications that I've made. I guess this is to the point of your kind of fit for purpose, right? Every
Correct.
simulation is need to be built or need to be customized based on what is the first point, objective. What is your intent of doing the simulation? Yeah.
That's correct. So I'm going to give you an answer which you might not want to hear. This is coming from Pak Novian, is it?
Yes.
How do I know whether this simplification is going to is going to make an effect? Well, one of the ways, let's say you're representing like an actual facility or something, then you can obviously compare your simulation results in reality. But that's, I mean, it just says, okay, it's different, but doesn't tell you why it's different. Why is it different? Well, that now we have to give it some thought. If I'm using something like HYSYS, Unisim, Pro2, or Symmetry, if I have like a steady state model for that, it is utilizing steady state thermodynamic models to represent the process. So transport phenomena effects may not come into play. If I have a distillation column, by default, each stage is a theoretical stage, which means that the equilibrium will be calculated, the mesh equations will be solved for each stage, mass will transfer immediately from gas to liquid and vice versa, and then it will disengage beautifully with no entrainment at all. Yeah. Whereas in reality, that doesn't happen. So how do we compensate for that? Well, in most simulators, you can add a tray efficiency, which is similar to, I mean, it's essentially a Murphy efficiency. In HYSYS, it was rewritten, slightly different. So if you take a look at the, I don't know if you actually have that in the manual, but in HYSYS, they did something a bit clever to avoid the calculation from crashing. But it's pretty much like a tray efficiency, or they'll even have like component efficiencies. Yeah. So the simplification that I don't have any mass transfer effects or any fluid mechanics containment effect, meaning that I now I have to lump it in a tray efficiency. If I have an existing facility, then I can tune it accordingly, meaning I can modify the tray efficiencies until I meet similar temperature profile as what I might see in the plant. Otherwise, Pak Novian, what we have to do here sometimes, if I'm working, say, for example, on a design case where I do not have any plant data available, then I just have to solve all the rigorous calculations. I have to do a hand calc. So I would take into account some of the transport phenomena. I do a hand calc for that, and then I would do a separate hand calc and compare with the simulator. Yeah, so there's no, unfortunately, there's no shortcuts around that. Yeah, so that's why that's one of the things we do. You either compare against reality, or you might have to come and actually do a hand calc, either a manual calc like that, or sometimes we actually write some additional code. I guess you can use MATLAB or you can use Python. It's got a whole bunch of mathematical tools these days. Yeah. So that's the only thing that we can do. And then sometimes, let's say, for example, if HYSYS can't do what we want it to do, then we will add on some additional functions, i.e. as extensions. So maybe, Fauzi, one day you can give a class, or I don't know, we could give a talk on like extensibility and programmability of HYSYS, because I don't think many
Yeah.
people use that. But you
Yes.
can add on that functionality yourself. It's you can add on additional features using this tool, or you can even use a spreadsheet, some customized calcs to sit on top of that. Yeah. So
Yeah.
unfortunately, there's no shortcut around that.
Yeah. I think on that point, another way also, Aspen has a tool called Aspen Custom Model, so that can be also integrated with
Yep.
HYSYS or Aspen Plus.
Correct.
Right. Next one is Naveed. He said, my understanding is that Peng Robinson fluid package cannot use for polar component. Okay. I have noticed that some people simulate gas processing applications containing ppm level of water with Peng Robinson. Is this acceptable?
That's an easy answer. The answer is no. You can't do that.
Right.
Yeah.
Yeah.
So as you mentioned, if you think about it, Naveen, again, I don't have the time to go through it right now. I actually do like a property estimation, fluid characterization class. I actually think that's in the similar. It's in that the Elsevier publication. I think it's under property estimation, applied property estimation. So Peng Robinson is primarily for nonpolar compounds. And if you notice the Peng Robinson equation, if you look at the structure of the Peng Robinson equation, it's a cubic equation of state. And where do cubic equations of state come from? The ideal gas law. So in back several hundred years ago, I can't remember when did the ideal gas law come out? In the 18 something. We had PV equals to nRT. Then van der Waal came along and then added a V minus B term and an A squared over V, an A over V squared term to account for molecular attraction and volume contributions, V minus V. But it's still on the gas side. It's not really doing anything on the liquid side of that. Yeah. So it's okay for modeling gas side or on non-polar components. When you're looking at the liquid side, where you have interactions like hydrogen bonds, then you need to work with an activity coefficient model. Hence, you can't use Peng Robinson to take a look at water at the ppm level. You need to go with an activity coefficient model, and you need to tune it properly. Yeah. So what are the other molecules in there? Because if you notice, if you choose an activity coefficient model and you look at the interaction page, the Aij, Bij, and the tau or Cij, sometimes some of those numbers may be blank. Yeah, so you need to you need to do some kind of regression to fill those numbers in. But hey, who has the resources to do those and calculate those interactions in the lab or buy the data and regress it? So 90% of us press the estimate from UNIFAC button. So you got to be careful, because when you hit estimate from UNIFAC, it uses the UNIFAC group contribution method, the combinatorial method, to kind of figure out what kind of interaction parameters would be at some temperature. So you need to be careful. So if you are really, really concerned about water, then you need to understand what the other components around there and make sure you use the right tool. So you might want to use maybe an activity coefficient model or some other model which is specific for that kind of application, but definitely not Peng Robinson.
Right. Okay, next one. I guess this is maybe any simulation checklist you can share for beginners. I guess this 10 is one of the checklists. Sorry.
That's one of them.
Yes.
Yeah.
Yes. Then Mr. Adam Aryan, I think this is related to the distillation efficiency we talk about, right? So in simulations of distillation column with trace, how would you account for the many factors that affect tray efficiency? Right. So I
That's a good
guess yeah.
that's a good question, because you only have one button. You've got maybe two things that you can do for this. Yeah. One is you can do what's in real. If let's say you have an actual number of trays and you've got a certain performance for that in the field, you've got actual plant data that's available,
Yeah.
and you try to model this in a simulator, you're going to find that you can't use the actual trays because HYSYS by default uses the theoretical trays. So there's two things that you can do. Either you can use a rule of thumb and take a look at the number of trays and use what's called a sectional efficiency. So let's say I've got like a column with a reboiler and condenser, maybe some kind of like a simple splitter with a reboiler condenser. Rule of thumb tells me for something like this, I might use a 60 to 70%. So if I've got like, say for example, 50 theoretical stages, when I translate that to my HYSYS model, I might just multiply that by half, 50 or 60%, maybe about half the number of trays in my simulation model. That would be like an overall sectional efficiency. Another thing that they have, and again, Adam, I think you're probably very experienced with distillation. There's a lot of these various factors, but in terms of what do we have in the simulator that we can tweak, the other one would be Murphy efficiency or tray efficiency. So in that case, you might have the actual number of trays, and you can attempt to tweak those efficiencies to account for that. If you're taking a look at your tray performance, it's going to be a function of a lot of things: the flow distribution, the fluid mechanics in the tray, the mass transfer. If you've got like some kind of internals, obviously all the internals that you make are designed to maximize the contact between the gas and the liquid in order to maximize the surface area. So you want to try to make lots of small bubbles. In the simulator, the only way that you can represent that, at least from my understanding, is either using a sectional efficiency, rule of thumb, or you can kind of tweak the Murphy efficiencies. Yeah. So that would
Right.
be
Okay.
the only thing that you would probably look at.
Yeah, I think I will skip the last question. I think we are past the time, right? So yes, I think everybody let's thank Rafael for sharing this tips, checklist, or whatever you want to call it, right? A best practice to help us build or maybe understand, build better simulation, use process simulations as a tool, right? Using it better, right? All right. Say okay. Let's type. Thank you, Rafael.
Thank you all
All
very
right.
much.
Yes, and don't forget if you have you can post like if you want just post one learning point from on LinkedIn what you have learned from these sessions from Rafael, right? Okay, and then we'll see you in the next webinar, right? It's next week. Sorry, the next week is actually Lunar New Year holiday, so it's on Saturday instead of on Thursday, right? Saturday morning Asia time, right? All right, that will be on gas processing, right? Okay, thank you, Rafael. Thank you, Rafael, so
Thank
much,
you so
right?
much,
Thank you
everyone.
all
Everyone have a
for
great
staying
evening.
back.
And for those of you
Yes,
celebrating
right.
New Year, Gongzi Fa Chai next year.
Go
Take care.
Sifashai. Right. Okay.